Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed this population dynamics modeling and how we can just formulate cell division model using a differential equation that we have discussed. And in that lecture, we have also discussed that how we can just achieve the steady state solution also. And the steady state solution that depends on resources available and this resources, how it is just acting inside the population growth level, that we have also considered. And in this lecture, we will discuss about continuous time models in a population dynamics. So, like for different structures, that is first we will just go for chemostat. In the last lecture, I have given the overview about chemostat also. And in this lecture, we will discuss about in detail how chemostat is acting for this population growth rate or decaying rate. Then in the second phase, we will just discuss about formulation of chemostat model, and in the third phase, we will just discuss dimensional analysis of a chemostat model, and in the final phase, we will just go for non-dimensionalization of chemostat model. So, if we will just go for the introduction of a chemostat, chemostat is nothing but it is a device used to study the behavior of microorganisms with limited resources availability. This means that the chemostat can be represented as the rate of influx of nutrients F into the system, and which can be accommodated within a volume V, and then it can be extracted out as a rate of efflux of nutrients F, and the total system whatever it is just occurring for supply of food and this the cells utilization and what is the output it is just coming, the total system it is called chemostat. So, chemostat is basically a bioreactor to which fresh medium is continuously added. This means that we can just say that if sufficient oxygen can be supplied to a medium, then this cells will be growth in a uniform way. So, if you just see our knee joints, there also this requires supply of external agents to get the activation of these lipids, and it should have a uniform growth for that. And this is basically called tissue engineering scaffolds or tissue engineering bioreactors. It has been used for chemostat process. And presently we are just discussing this chemostat, which is just used for culture of the cells. So, culture of cells means two types of cell cultures it is used naturally. It is one, it is called continuous culture technique, one is called batch culture technique. And we are not going in detail for that, but for in a general sense, if we will just discuss here, chemostat is basically a bioreactor to which fresh medium is continuously added, as I have explained. Suppose oxygen is supplied and the liquid inside chemostat is continuously removed in order to keep the volume inside the chemostat constant. So, whatever it has been, since the container or the volume it is constant there, so according to the conservation of mass, whatever this amount it has been supplied, the same amount it can be flux out there. And the liquid inside the chemostat should be well mixed, so that conditions are homogeneous or uniform, and this make it a self regularized. That is, when nutrients are more than microorganisms, it accelerates their growth. Definitely, if it will not properly mixed, then we cannot find a uniform structure of this all the medium there, and this growth will be hampered. When they are in sufficiently large numbers, they compete for nutrients and make them to reduce in number. Since the total volume of chemostat should be constant, this make nutrients to increase. This process repeats in cyclic manner in order to keep chemostat volume constant there. That is, at steady state we can just find that in a cyclic form we can just find that always we will have a constant level, it should be maintained there. and this concept of chemostat is widely used for drug delivery systems, especially when this drug delivery is applying, then there is a uniform distribution of this nutrients or this chemical or whatever this drugs it should be supplied to our body, it should be maintained. So, if you will just go for this mathematical representation of a chemostat, then already in the last lecture we have discussed that this growth of population level, that is defined as a dn by dt, which is written as like a k into n of t, where this k is the like a rate of change of population at that level we have just considered, where if the resources are available or this C is the concentration of resources we have just considered, then we are just considering k as a function of C there, and our model is directly defined as in the form of like k n of t, okay, dn by dt. No? So, dn by dt it is just defined as in the form of k into n of t, and where this k is dependent on like this concentration level or C is available there or the resources available there, and even if this population level it is just changing with respect to time, we cannot say that this population growth rate it is just actively participate or actively it is just occurring inside the system, since if we will just see here we have just added a factor minus fn here. So, which represents the total mixed outflow there. This means that inside a container and inside a volume, whatever this change of population with respect to time, if you will just consider that that depends on this total population size n multiplied with this like proportionality constant, and whatever this outflow it is just occurring over there also. Outflow means we can just say that the flow in there with the nutrients, and it can just take out some of this concentration of the population from the system also. So, that is why we are just writing here the total mixed outflow as defined as flow rate of f into the concentration of population n there. So, maybe some dead cells are there or some of the active cells that can be removed out with the flow there, and we are assuming that bacteria are properly or well mixed with resources in chemostat. This is to make like mixture of resources and bacteria to be spatially independent, and hence they are only depending on time, and therefore the model will be formulated by ordinary differential equation. Since we are just considering here this is change of population or the change of cell number, that whatever it has been just change with respect to our proportionality constant with the total population size, and whatever it has been efflux out from the system. And now think if we will have like a non-uniform distribution or it is not properly mixed inside the system. So, many constants it will just come into the picture, that maybe in the next slides or in the next lectures we can just consider many restrictions it will be just followed to deal that model. Similarly, in the second equation if you will just see here that we have just assumed this concentration or the limited resources whatever it is just available there, that will just also get changed with respect to time, since this cells that will just consume these concentrations, and this concentration change which effectively dependent on this minus alpha kcm that we have just discussed in our previous lecture, that resources it will be just used by these cells. So, that is why it will just get like reduced there depending on the population size n, and finally we are just adding a term that is minus fc, which is represents the decaying of total resources or decrease of the resources, and fc0 we are just adding an extra term which is just depending on the initial storage of resources, that depends on whether it has been used by the cells or some remaining portion it has been used by the cells and it is kept there, that depends on plus fc0. So, if you will just go for this dimensional analysis of this chemostat equation, we can just find that this equation n dash t which involves k, n and minus Fn there, that is the flow rate out, and which can just take out the total population size, or the population size, sum of the population size, it can be just taken out. And if you will just see here end s t is nothing but which can be just defined as a dN by dt there, and dN by dt that depends on this number per volume over time. This means that this change of number of population that completely dependent on this volume of the container, and with respect to time how it is just getting changed there. So, that is why this dimension it can be just defined as a number per volume into time, and K of C, that is your rate of change of population level, that depends on time only. So, that is why it has been defined as 1 over time there, and the number means that is a total number of population or the total number of cell size, that depends on the number for volume there, and F, that is a flow rate which depends on this volume over the time. And if you will just substitute all these dimensions in this equation here to verify this correctness of equation, since it is very essential to do this dimensional analysis for all of these differential equations to get a solution. So, we can just find there is a inconsistency is preserved inside the system, since if you will just put all these dimensional numbers inside the system, we can just find that this whatever this dimension we will just get in the left hand side, this is not equal to the right hand side. So, that is why it is a imbalanced system or a inconsistent system. To correct this problem, we need to divide the flow rate F by the volume V there. So, practically we should define the flow rate for unit volume instead of a flow rate for flow rate. So, for that what we will do is we have to correct this chemostat model, and for that what we will do is we will just divide F by V in the right hand side, and then we will have like a corrected equation here. Since if you will just see here, the left hand side it is number for volume into time, this equals to K is 1 by time into N is the number per volume minus F is the volume per time into N, it is a number per volume into time. So, if you will just see here volume can we cancel it out. So, this left hand side this is number per volume into time, this equals to number per volume into time minus, if you just see, number per time square only. So, if we want to find in a complete sense here, that is number per volume into time, number per volume into time. So, this one is a number per time square here. So, F is defined as here volume per time, F is volume per time, then we will have like N, it is a number per volume, this one, sorry this one not time, number per volume here. So, this will be time here, number per time only. So, we will see now this number per volume into time, this equals to number per volume into time minus number per time here only. So, that is why there is a discrepancy of or there is a like a deficit of this volume here. So, that is why we have to like divide here volume to get it in a complete dimensional situation, or to analyze this correctness of this dimensionality, we have to divide the volume in the final term. So, if we will just divide this volume here, then we will have this equation like dN by dt, which is defined as Kcn minus F by V into N there. So, now we can just have a complete dimensional model. And if you will just see this second equation here, that is just defined as like C dash t equals to minus alpha k n minus Fc plus Fc0. We can just see that this C dash T, or like a concentration with respect to time change, which can be just defined as a mass per volume into time. This equals to alpha, which is defined as a mass per number, into k, k is defined as like 1 by time, into n, which is just defined as a number per volume, minus this is F by V, F is written as volume per time, into C, C is defined as here mass per volume, divided by V here. So, V is defined as volume here, plus F by V. If you will just see here, F is written as also volume per time, and into C0, C0 is nothing but a constant here. So, divided by volume is defined as volume here. So, if you will just see here, so first one it is mass per volume into time, then this is also mass per number into time, number it will just cancel it out. So, we will have now mass by volume into time here. Then if you will just see here, then volume it will just cancel it out. So, if you just see here, this is a mass per time into volume, and if you just see here, this is just defined as F is a volume per time by volume into C0, which can be just written as a mass per volume here. So, volume cancel it out. So, this will just give you mass per time into volume. So, now it is perfectly equal for dimensional analysis. So, finally, we will have this mass per volume into time, this equals to mass per volume into time, minus this is a mass per volume into time, plus this is a mass per volume into time. So, perfectly equal. So, if you just go for further analysis of this chemostat equation, we can just find that this is dimensionally correct now, and in the previous model we have analyzed the rate of reproduction per unit time K was linearly depending on the resource of concentration. So, already we have defined that one K as like Kc we can just define, and this implies that for high amount of resources the bacteria population will go on increasing. Since if the available resources it is sufficient there, then this population level will grows it off. So, does it happen practically? Especially no. Since if you will just see here, we need a function K of C in such a way that it has some saturation limit. Resources are available up to certain limiting value. After that you can just find that whatever these resources, it will just grow up or it can just come to the picture, then it can be utilized in a uniform manner. Especially if you will just see that suppose one deer population it is just existing for a practical sense, if you just see, and suppose available grass it is there. So, then this deer population it will just get increased if sufficient grass is available to them, and if suppose this deer population level will get increased in a high level, then there will be a shortage of grass, and after certain time you can find that they will just struggle each other to find the food, and some of the deers will die out there, and if some of this population will die out, again this resources it will be available there, since the grass will like grow up and it will be like up to a level that these deers can eat, and this will just balance this nature in such a fashion that this resources will be available to them in such a manner that we will have a like linear growth rate. And if you will just consider such type of models, then one such type of function it is just considered in the form of like K of C, where this available of resources or this concentration which depends on this rate of change of this population, which is defined in the form of K max into C by Kn plus C, where Kn is a constant parameter which balances this k max value and c value here. And this function saturates to k max when kn tends to 0. If you directly we will just suppose to put here kn tends to 0 here, then k of c, especially this is tending to k max here, since c by c equals to 1. And if you will just assume that c equals to kn suppose, then the function will half of the saturation value. So, this function is defined in such a fashion that either a maximized value or it will just give the half of the value of the saturation we can just achieve. And in the graphical sense, if you will just visualize this one, so it is just represented in the figure here, and this function is known as Maclaurin-Maintain kinetics, and this model with this kinetics will be given as like, if you will just replace here dn by dt as kcn minus f by vn here. So, it can be written as k is replaced by k max into c by kn plus c here into n minus f v by n, and dc by dt it can be written as like minus alpha into k. So, that is why k max c by kn plus c into n minus f by v c plus f by v c 0 here. Now, if you will just observe these equations, the parameters, if you will just see here, the parameters are like k max here, then kn here, then f it is present, then v is present, alpha is present, and kn it is also present there. So, two more times we have just written here kn. So, k max, then f, v, alpha and kn. Now, let us do this non-dimensionalization to reduce the number of parameters, especially we have just discussed in one of our earlier lectures about this non-dimensionalization things, when we have just used this discrete logistic model. So, there we have used this reducer parameters to get this 2 parameters to 1 parameter solution there. So, especially this non-dimensionalization is made to reduce these parameters. To reduce the number of parameters, let us rescale all the variables, that is in the form of like n equals to n star into n1 here, and c equals to c star into c1, and t equals to t star into t1. If you will just see here that n star is the new variable, c star is the new variable, and t star is the new variable c here. And especially we can just write this variable n star as n by n1 here, and c star can be written as c by c1 here, and t star can be written as t by t1 here. And if you just see here, all these variables whatever associated now newly, that is n star, c star and t star, all are like dimensionless variables here. And if you will just see here n1, c1, t1, all are parameters which are taking this dimensional values here. This means that if n has certain dimensions, n1 has also certain dimensions, and if c has certain dimensions, then c1 has also certain dimensions. And when we are just reducing directly to the variables in the form of n star, c star and t star, which will provide us a new equation which is free from this like dimensional variables. And the chemostat model with new variables, if you just put these variables in the equations, then directly we can just replace here n by n star into n1, and d by this t can be replaced by t star into t1. Similarly, c can be replaced by c star into c1, and n can be replaced by n star into n1. So, similarly we can just replace in the second equations also. The non-dimensional form of this equation can be written as in this form here. And since all of this n1, t1 and c1 all are constants, so we can just take out these terms outside these differential operators, which can be written as n1 into dn star here, and d of c star c1 it can be written as c1 into dc star, and d of t star t1 it can be written as t1 dt star here. So, after putting all these terms, finally this equation will be reduced in the form of dn star by dt star. If you just see here, so this n1 and t1 it has been taken out, and obviously it can be multiplied in the right hand side as t1 by n1 there. So, t1 by n1, so that is why n1 got cancelled it out, and T1 it is just multiplied there. Similarly, in the second equation, if you will just see here, so T1 if you will just multiply here also T1 by C1, the same one we have to do here also, T1 by C1 here. So, it can just cancel it out, and T1 by C1 it can be multiplied here. So, C1 it will just cancel it out, and C1 it will just cancel it out here. So, that is why T1 can be multiplied here. So, T1 can be multiplied here, T1 can be multiplied here, and C1 obviously it will be there. So, this is the factor completely you can just get. Now, if you will just see here, the total number of parameters involved in this model are like T1, K max, K n by C1, F by V, alpha and C1. So, the total number of parameters are still same, but some of these parameters has been changed since this division of terms are there. If we substitute, suppose here C1 equals to Kn, since Kn is the arbitrary parameter and we can just change according to our flexibility. So, if we will just replace this Kn by C1 here and T1 by V by F, we will get rid of 2 parameters here, and thus we will leave with only 4 parameters here. And now, if we will just proceed that we can just consider N1 in such a fashion that alpha N1 into T1 into K max by C1 equals to 1, suppose, if we will just consider for a like a particular case. Then we will have like N1 can be calculated as C1 by alpha T1 K max, which can be written as also Fkn by alpha K max into V. So, if you will just do this new model after this non-dimensionalization, it will be reduced in the form of like dn star by dt star, this equals to alpha 1 C star by 1 plus C star. If you will just see the previous model here, we are just replacing all these variables in terms of this alpha n1 T1 K max by C1, this equals to 1 there. So, that is why this will be reduced in this form here, that is dn star by dt star equals to alpha 1 C star by 1 plus C star n star minus n star here, and dc star by dt star, this can be written as minus alpha C star by 1 plus C star into n star minus C star plus alpha 2, where alpha 1 can be written as like V by F K max and alpha 2 can be written as C0 by C1. So, here we will have like only 2 parameters alpha 1 and alpha 2. Now, all the parameters and variables are dimensionless. So, easily we can just obtain the solution. So, we will write the same model without, since this n star or any parameters we can just put there. So, obviously we can just replace star as in the form of like n there and C star as C here. Then obviously this model will be reduced in the form of dn by dt, this equals to alpha 1 C by 1 plus C into n minus n, and dc by dt, this is just represented as minus C into C star is replaced by C here. So, that is why C by 1 plus C into n minus C plus alpha 2. So, in this lecture we have discussed about this chemostat modeling and how we can just develop a chemostat or a bioreactor using this cell culture technique, and which is restricted that the medium should be properly mixed. We have not considered the inhomogeneity or inhomogeneous mixture here, and which restricts many conditions. So, that is why we have not considered that one, and we have just considered that these resources should be properly mixed with bacteria suspension to avoid the spatial dependence with respect to time. It should have a uniform change, and if it does not happen, so then it will lead to a partial differential equation instead of ordinary differential equation. And in the second phase we have just discussed the different equations which is in the form of a differential equation and which can be used for the formulation of a chemostat model. Since in the earlier model we have not considered this outflow conditions, that if there is a inflow of all of these resources or like some of these cells, so efflux conditions are like outflow conditions we have not restricted. So, that is why this formula has been get changed, or this formulation of a differential equation got changed. And then we have tried to non-dimensionalize this chemostat model with various parametric values, And finally, we have obtained a non-dimensional equation based on this total number of population size, or like this total number of cells with this limited resources of concentrations. So, in the next lecture maybe we will just go for the solution of this chemostat model and all other stuffs. Thank you for listening this lecture.